Let's solve this homogeneous equation. And yes, it's already identified as a homogeneous equation on our previous video pertaining onto that. Please try to visit our channel and view that video for your own consumption, because here we're going to proceed immediately on the process of solving this, because it would take us time in solving for homogeneous equations just like this, because we're going to use here the appropriate substitution. In the sense of substitution, we're going to decide which of the variables x and y will be represented with the other and introducing another variable. We are going to do this because we are going to find a way to solve this homogeneous equation where we could just easily use the separation of variables. X could be represented by vy, where we introduced v, or we could also have y is equal to vx. It depends now on which will be used, because we're going to look at our equation in which of the two annotations, dx or dy, is paired with easier or simpler expressions. In this case, we could see that dy is paired with x squared, which is simpler than this form here. In short, we're going to look at dy and we're going to use y is equal to vx. Okay? So that later on, we can just easily substitute this on our equation. So, if y is equal to vx, again, we used y because it's dy, which has easier or simpler expression x squared, or minus x squared specifically. So dy here, or the first derivative of y, which is equal to vx, is the derivative of the product v and x. So you can have this expression, v times the derivative of x plus x, the derivative of y. That's how we solve the derivative of a product. So we're going to use both of these expressions as we substitute it on our original homogeneous equation. So we have here y squared plus yx dx minus x squared dy equal to 0. And again, we're going to let y is equal to vx and dy equal to this expression. So y, that's actually vx, or the square of y, or square of vx, plus another y, which is vx, times x. That's just for our first term, dx. Again, y becomes vx and another y here. Next, minus x squared, and our dy is changed to this. You will have v dx plus x dv. This is equal to 0. Now, the next thing here is to simplify all these terms and probably distribute it here, because there might be some expressions that may be cancelled on the process. So here you will have, let's start first. Sorry for that. Let's start first with the form of this. So you will have v squared x squared plus vx squared, that's for dx alone. And then you will have here minus x squared v dx plus x dv. So again, distributing all these terms, you will have v squared x squared dx plus v x squared dx. Nak, kinahi gamay nak, salamat. Then distributing this, you have minus x squared v dx, or arranging it alphabetically, you could also have here vx squared dx plus x cubed dv equal to 0. Take note, as we did that, we'll have these two expressions which can be cancelled out. Hence, our final form after our substitution is x squared dx plus x cubed dv equal to 0. This is just the first form after our substitution. Now that we are done with this, the next thing here is to use the process of separation of variables. Hence, we would like only v for dv and x for dx. To do that, what we can do here is, since we don't like our v squared here, we're going to multiply this entire expression with 1 over v squared, so that would be cancelled here. At the same time, we don't like x cube here, so we'll have to divide this x cube as well. So with that, on our first term, this will be cancelled. You have x squared divided by x cube. That's basically equal to dx over x. Please try to review that one. Then plus, as we take the x cube here, you are left with dv over v squared equal to 0. Or you can rearrange the v squared. You have dx over x plus v to the power of negative 2 dv equal to 0. We are done separating the variables. This time, we are now going to integrate both sides. We did not change the first term as to x to the power of negative 1 because we have a formula for that. The second one is we change it to that we can use here the concept of the power. Of course, this is derivative of 0 as well. So we'll have here the derivative of the integral of dx over x is the natural logarithm of x. And here plus you are expecting here to have v to the power of minus 1 over negative 1 plus c. But let's not introduce c there because we're also going to introduce c on the other side. Even if you will have c and c here, they will just be moved on the other side and combined with the larger c. So no need to do that. Okay? Just for the final form, you will have here the natural logarithm of x plus 1 over v is equal to our c. So we are almost done. It's already okay here, but what was v earlier? The v earlier was taken from this expression y is equal to vx. So in short, v here is just y over x as we solve for v. And that's the expression for v here. So we have the natural logarithm of x plus 1 over y over x is equal to c. Let's simplify this. We have the nested rational expression. So you have the natural logarithm. You can do the keep change flip method here. X over y is equal to c. Okay? Now, if you don't like y or a rational expression here, of course, you can multiply all terms by y so that it would become the final answer is y, natural logarithm of x plus simply x because we removed that plus, or sorry, equal to, that's equal to cy. Now, at this time, it's okay to have an answer like this, okay? Because, or if you would like in terms of x, so you can move it on the other side, but this is already okay. We have now solved this given homogeneous equation. And this was the process using the concept of substitution. Thank you very much for watching.